Hello, my name is Dr. Elena Samonina from University of Virginia. Today, I will demonstrate a powerful tool that can accelerate the process of grouping food additives based on their structural similarity and toxicological profile. Let's begin by exploring the publicly available research developed by the U.S. government, and this is Environmental Protection Agency. This extensive database includes information on over 1,200,000 chemicals. To illustrate the workflow, we'll start with common food additives like ethyl gallate. And this particular compound was recently banned as a food additive in EU. Once we locate ethyl gallate in the database, we gain access to a dashboard, which includes a structural synonym, related substances, and a toxicity overview. While there's no cancer classification noted, we do see the documents on acute toxicity, as well as skin and eye irritation. Now, what makes this tool particularly useful is its ability to identify structurally similar compounds based on Tanimoto coefficients above 80%. Platform retrieves a list of close analogs, over 300 in its case. To refine the list, we apply a filter for qualification control, level 1, which ensures the high confidence data. This narrows the list to just 23 compounds. Next, we examine another very powerful tool, that is TOXCAST data, which provides insight into how biologically active each compound is based on hundreds of in vivo assays. So, for example, lauric gallate shows 49 activity rate. So, it was presented activity in 179 assays out of 365. Octyl gallate exhibits similar high activity. This high biological activity suggests a red flag for potential toxicity. Although activity alone does not equal hazard, it does warrant closer examination. Now, we're going to use another very important tool developed by the EPA called the Generalized Read Across, or GENRA. GENRA enables us to search for structurally similar compounds and predict potential toxicity by examining their neighbors. And these neighbors are chemicals with similar molecular features. These neighbors are identified based on structural similar metrics, and GENRA uses existing literature and empirical data to help predict toxicological outcome for chemicals with limited or no direct testing. This read-across approach is incredibly powerful when prioritizing chemicals for further review or regulations, especially in food safety contexts. Let's now explore structural analogs of ethyl gallate. Using this tool, the read across, we can identify compounds like gallic acid, lauric gallate, octyl gallate, salicylate, ethyl parabens are structurally similar. This implies they may also share similar toxicological properties. By running GENRA cross-read analysis, we can examine how many peer-reviewed studies are available for each analog, predicted or observed acute toxicity values such as LD50, or biological activities levels across various assay systems. So, we have now combined data from two powerful EPA tools, COM-TOX and GENRA. This integrative approach allows us to evaluate both empirical toxicity data and structural-based predictions. Let's break down the findings. While octyl gallate and propyl gallate, their LD50 dose is very similar, around 2,000 milligrams per kilogram. The lauric gallate appears to be less toxic, with LD value nearly twice as high, indicating a higher tolerable dose. Ethyl gallate is banned in EU and not listed in the US. The propyl gallate is approved in both countries. The lauric gallate and octyl gallate is banned in EU but approved in the US. This leads us to critical questions. Why are some structurally similar compounds banned while others remains approved? When we cross-reference LD50 values with biological activity data from TOXCAST, we find a key difference. Lauric gallate and octogallate show very high biological activity, 48-49% assay positivity, while the propyl gallate, in contrast, has relatively low biological activity, making it less concerning despite its structural similarity. Now, let's circle back to another compound class structurally related to ethyl gallate, the parabens. We have already seen that parabens and gallate share a common core structure, different mainly by their side chain. Methyl, paraben, propyl paraben, butyl paraben all exhibit similar toxicity. However, ethyl paraben is twice as less toxic than the three other examples.
The methyl paraben and ethyl paraben are approved in Europe. However, propyl paraben is banned, even though it differs from ethyl paraben by just one carbon in the side chain. In the United States, all parabens commonly used in food, methyl, ethyl, propyl, butyl, and even haptoparaben, are considered to be generally recognized as safe. The graphs. Why is propylparaben banned in EU while other structurally similar compounds are not? Again, the answer lies not just in LT50 values, but in biological activity. TOXCAST data shows that methylparaben and ethylparaben have very low biological activity, which is around 3%. On the other hand, the propylparaben, butylparaben, and haptoparaben show increasing biological activity, with haptoparaben being the most active with 30%, 35% toxicity. When we examine the parent compound, or hydroxybenzoic acid, the base molecule for which parabens are synthesized, it showed the zero biological activity. This likely explains why it's approved for use in both the EU and US, often as a flavoring agent. In this brief exploration, we demonstrated how
can be used together to analyze food additives through the lens of structural similarity and biological activity. This integrative, evidence-based approach empowers researchers, regulators, and food safety professionals to make more informed decisions about the safety and grouping of chemical substances. Thank you for watching.